Hello and welcome to Felix and Kit's exploration of the explanation of respiration. We're going to be starting off with glycolysis, which is of course the conversion of glucose to two molecules of pyruvate. The first step requires an ATP molecule to phosphorylate the glucose. This of course prevents the glucose from escaping from the cell. Without it we'd be pretty stuffed. The glucose that has been phosphorylated is then transformed into fructose, an isomer of glucose. The third step is, of course, the rate-limiting step of the entire process as a whole, as it requires PFK, and that is the slow train on this carriage, on this journey. The glucose, or rather the diphosphate fructose, is broken into two different 3-carbon-long molecules, which end up both being used later on, even though only one of them is applicable in the later processes we're now seeing. The one that is useless is changed by a catalyst to be useful. The next half, I suppose, of glycolysis requires an NAD plus and two ADP molecules. These two ADP molecules undergo substrate level phosphorylation, where they are transformed back into ATP. The whole process rears two pyruvate molecules, because of course the pyruvate creating half can occur twice, because you have two 3-carbon long molecules that you can use from it. Onto the link reaction. This is all happening in the matrix now. The link reaction, glycolysis, happens or occurs in the cytosol, aka the cytoplasm. We can see here the pyruvate is eventually transformed into a single molecule of acetyl-CoA. The link reaction is very simple. There's a decarboxylation, which produces a carbon dioxide molecule as a waste product, and the outcome of that is that the pyruvate loses a carbon atom and goes from a 3-carbon chain molecule to a 2-carbon chain molecule. NADH is also created along with the proton from an NAD plus molecule onto the Krebs cycle. The Krebs cycle occurs inside the matrix and requires an acetyl-CoA molecule which has 2 carbons. The acetyl-CoA loses its acetyl group and bonds with an oxaloacetate molecule to become citric acid, which has 6 carbons. There is a loss of a CO2 known as decarboxylation, and that helps to reduce an NAD plus molecule into an NADH and an H plus, which is of course a proton. This whole process is repeated in the second step. In the third step, the 4-carbon molecule is used to help phosphorylate GDP into GTP, which later becomes ATP, which is very useful for us. And the resulting molecule is known as succinate, which is used to reduce FADH into FADH2. There is then a hydration of the 4-carbon molecule, and NADH plus is again reduced to NADH. The outcome of this is 6 NADHs, 2 FADH2s, and 2 ATPs, because of course the whole process. Move into now the big energy producer of respiration, oxidative phosphorylation. The NADH breaks up into an NAD plus and a proton, as well as an electron, which is using the electron transport chain. The FADH2 and the Fa becomes FAD and is used in the second protein complex. There are 5 protein complexes in oxidative phosphorylation. The first 3, and actually the fourth one as well, are used in the electron transport chain, which is used to help maintain a proton gradient, on the other side of the membrane. This proton gradient is used for the proton motor force, which helps to phosphorylate ADP into ATP. There's a net production of 31 ATP, which is much more than everything else, and the oxygen helps to mop up all the electrons. Bye for now.